When I was in high school back in Bulgaria, we had this last exam called the Matura. And the Matura is something like the A-levels they have here in the UK. But before the end of the last year in high school, every student had to choose a specific subject they would like to take this Matura in. So me, an intellectual, decided to take the Matura in biology because I thought it would be the easiest. Needless to say, I did not do good in that exam, but it sparked an interest for life, and that interest was in the so-called molecular biology, or genetics. So I made my application and decided to study biomedical science, because I thought it would be easier than medicine. But throughout the years when I studied biomedical science, I stumbled across a man called Frederick Sanger. Now Sanger was a very smart man. He was a Nobel Prize winner, he was a father, which is great. But the invention that he was most known about was called the Sanger sequencing. This is a very long, confusing and complex process of separating the DNA and reading it like a sheet of paper. And people like me on the internet just come here and talk about sequencing and DNA and nucleotides. Just imagine for a second how complex this whole procedure is. So I'll try to explain it to you. So this is where this comes in. My whiteboard. Sanger sequencing can be split into different parts, but the first one is extraction. So the extraction process is very simple. You take a cell, or nowadays we take saliva, and you basically want to separate the thing that we want, which is the DNA, from the things that we don't want, which is the other molecules in there. So how do we do that? We put this sample of saliva into a centrifuge and we spin it really fast. That's how it works. So once we separate everything that we want and we don't want, we put the DNA into another sample and we try to replicate that DNA to reach millions of samples. This process is called replication. This is already mind-blowing, like who would have thought about that? But the next step in the process is called denaturation. Denaturation is basically separating the twin DNA strand into two single strands. How does that work again? Well, you put enzymes, single enzymes, which we don't know how we got, into the mixture with the DNA. And the next step of the process is called annealing. So basically what annealing is, since we have the two single strands now, we put primers into one of the chains, or every chain, but we put primers which are radioactive, which will give us some kind of an indication where that strand ends. So how do these primers know exactly where to be glued to? Enzymes. How do they actually do the gluing process? Enzymes. So when you have the radioactive primers onto the chain, we go to the next step, which is called the elongation. Now, elongation is basically the addition of the so-called dinucleotide triphosphates.
Bro, what are you talking about, man?
Now here it gets a little interesting, and that's why I have my whiteboard to explain it to you. So we have a normal strand, right? A normal strand right here. And at the end of the strand, right here, we start adding the dinucleotide triphosphates. So we have four for the four letters, A, G, T, C, right? And here, we start, when we add all the dinucleotide triphosphates in the mixture, they start adding up to the chain. It's a random process, completely random, but every dinucleotide triphosphate that adds up to the chain stops the production of more nucleotides in the chain. So what does that even mean? It means that you have millions of chains inside that mixture, right? So every chain will start adding different types of dinucleotide triphosphates. And so every chain will be longer and longer and longer, or shorter and shorter and shorter, and we'll have every kind of chain there is. And when we start analyzing these chains, we'll find out what kind of dinucleotide triphosphates got attached here, which allows us to read the chain. Does that make sense? Right? It does? No? So once we have those millions of different strands ended at the second letter, the third letter, the fourth letter, every single letter in the chain, you can actually read the whole strand. So the next step of the process is called the electrophoresis. Now, electrophoresis is basically a lab procedure which separates molecules by size and charge. there's a gel inside, and once you put your mixture in different types of wells, you activate the machine, and for like 4 to 6 to 8 hours, you start separating the molecules by size and charge. Maybe that wasn't a good explanation, but let me just try to explain it thoroughly. So basically, this is your electrophoresis here, and everything right here is in gel, and you have your molecules here. You have the whole DNA sample is in like, what, 5 wells. You start the electrophoresis machine, you put the charge in, right? And these molecules start moving over, what, 5 hours, maybe even more. And they stop at a specific space in the gel, and that determines what kind of a size they have, what kind of charge they have. So that's what electrophoresis basically is. And since now we've determined which molecule is what and where and how much it weighs and what charge it has, you can now analyze this whole gel, see what kind of a strand we have. And this basically is printed out as a sheet. So it looks something like this here, right here. So you have one adenine, one thymine, you have adenine again, you have guanine, you have all those nucleotides here. And if you add them onto a one strand, it would look something like that's your whole strand, because now we can read it, because we couldn't read it before. Does that make sense? Maybe yes? No? But this was something like the first ever procedures combined into one procedure called Sanger sequencing, which can actually read your DNA. But later on, a couple of years after that, people started innovating. They tried to make the whole process cheaper, more time efficient. And 35 years after that, companies like 454 Life Sciences, Illumina, Oxford Nanopore, they all started making or producing solutions to that kind of problem. And they came up with a technology or a procedure called next generation sequencing. And this is actually where it gets very, very interesting, because when you speak about next generation sequencing, you need to speak about one man who studied this technology all his life, the master chef himself, Dr. George Church. This man started cooking back in the 80s, and he's never stopped since. Now let me tell you a little bit about Dr. George Church. This man has spent more than half of his life in Harvard Medical University, either as a student or a lecturer. Back in the late 1990s or the early 2000s, when I haven't even been born yet, he was a major force to push the Human Genome Project, which is a quite a revolutionary project if you ask me. For those who don't know what the Human Genome Project is, a whole bunch of scientists from different countries came together and tried to map the genome of the human body. And they kinda did. So fast forward 20 years to Dr. George Church's new company called Nebula Genomics, where this whole technology, the whole genome sequencing, is available to individuals for a very cheap price compared to 20 years ago. What you can do now is buy a kit, put your saliva sample into the tube, send that tube back to their labs, and you can get your whole genome sequenced. What? But the question is, who cares? Why would you even bother with that? Well, this test actually shows you your future of disease. But give me a second just to explain how it works here. So DNA is permanent, right? You've been born, you have one set of DNA, right? 46 chromosomes in every cell, and that's it. Now, you have epigenetics, which just modifies the genome. It doesn't change it permanently. It just modifies between like whatever environment you live in, right? But the whole process of this kit is, again, you put a saliva sample in a tube, you send it back to their labs, which is in America, and they sequence it, replicate it, right? They read your whole DNA, which is about 3 billion letters, by the way. They put it into a digital file, which is about, what, 60 gigabytes? Quite a lot, right? And what they do is they put this digital file and compare it to a million other individuals, see how much proneness to disease you have in comparison with the other people. And this whole digital thing is encrypted, and it's encrypted with a blockchain technology, which I know nothing about, but apparently it's really good. And once you have these millions of individuals or individual files of whole genome sequencing, you compare it in a sense to a article that is peer-reviewed, that is known to be right, and then you can measure the proneness to any disease. Now it sounds very difficult and complex, but you can see it on their website. I'll try to give you a picture right here. It just shows you the study, it shows you the percentage of proneness you have to the disease, and that's pretty much it. Before I graduated in 2023, I bought this kit to just learn about the technology because I was interested. And I can just show you my proneness to disease right here, right now. And yeah, take a look at that. What's that? Depression pathophysiology. That's just great. This kit can also show you some different traits that you might have. As you can see here, I might be more prone to greater than average longevity. Who knows? If we go to Ancestry, you can see that I have a predominantly East Mediterranean genome, which means that I could be more Jewish than the Armenian that I am. Take that as you may. And most importantly, you can download that digital file and maybe browse your own genome if you actually know how to do that. And the great thing is, the whole file or your genome stays the same throughout your whole life. So the file is the same, so you can use that file throughout your whole life. Isn't that great? But let me tell you another story really quickly, because I believe it will explain why this technology is important at basically any age that you choose to do it. A couple of years ago, when I was at university, I had this subject called Omic Technologies. Now, Omic stands for Genomic, Transcriptomic, Metabolomic, all of these fields of science connected all into one subject because they're all connected into real life. And one day, my good professor thought that it would be a great idea to show how these fields of science save real lives. So she went back to her computer, browsed a couple of folders, and she sent the whole class a case study about a baby, and that baby's name was Oliver. Oliver was under 6 months old, and he was a ray of sunshine, a very joyful kid, but he had some health problems, so his parents just took him to the hospital. Now, a doctor, after a blood test, found out that he had a small lump on his right leg. Unfortunately, a lump at any age, at any point in time, normally means that it's cancer. And cancer at this young age is extremely dangerous because babies don't really have that developed immune system. The doctor, however, made a hopeful decision to not proceed with chemotherapy, which is the normal procedure in cancer treatment, but to do a test called whole genome sequencing. Now, the parents agreed to it. The whole test took more than 40 hours, but when the results came back, something really interesting happened. The doctor went to the troubled parents and he told them that he found out that this lump not only is not cancerous, but it will disappear in time by itself. Just amazing, isn't it? It really is something to save a human life and to improve the quality of life of the whole family as well. That's why I believe that this technology can save lives. And it has. But I also believe that it's quite dangerous. What do you think? Let me know in the comments or just message me on Instagram. Thank you for watching.